So the title of this lecture is Polymer Matrix Composites, More Than Just Strength Improvement. And the reason why I titled it this is because we're going to look at other ways, other applications we can make, or application we would make composites for. And when most people think of composites, they think of strength, they think of improvement, and with a good reason. And if we go back to the earliest use of composites, we need to ask ourselves first, what is the first documented use of composites? And if you look at the Bible, Exodus 5:7, the Pharaoh tells his people to no longer supply the people with straw, the people being the Israelites, for making bricks. Let them go and gather your own straw, or their own straw. And this was after Moses came in and said, let my people go, pretty much. And this was punishment on the people of the Israelite slaves, really, imposed by the Pharaoh. Now, it's very interesting because they're talking about straw for making bricks. And so the straw was actually used as a reinforcement. So no matter your religious belief, the Bible is still a written document. And it was written over 3,000 years ago. So over 3,000 years ago, people were making fiber reinforced composites. And you may think it's old technology, but if you look at this paper, people are still doing research on reinforcing straw with, or using straw as a fiber reinforcement for bricks. And so this paper was published in 2017, which isn't that long ago. And so from the get-go, composites were made as more of a strengthening type of application. And the earliest case is strengthening of bricks. And you can go into other strengthening mechanisms for bricks. You always hear that the Greeks sun-baked their bricks and the Romans oven-baked their bricks, but that's more manipulating the matrix. Reinforcing with straw would be making a composite, whereas the matrix is clay, pretty much. And if you look at straw reinforced bricks, it's pretty much the same thing as adobe. And excuse me, if you look at this building here, this is a building actually near my home, and it's an adobe building, and then they put stucco on it, kind of a veneer, and it's kind of flaked off, and you can see the adobe bricks. And so straw reinforced bricks is what we see in adobe. And adobe's been used in the Southwest for centuries by the native cultures, or the indigenous cultures. And my child, this is my hand, but I'm holding a brick my child made, had kind of done an experiment making her own adobe bricks. And if you look closely, you can see it's essentially a plant fiber reinforced ceramic matrix composite. What a mouthful. That's kind of a segue into what we're going to be talking about today. We're going to talk a little bit about plant fiber reinforced composites, research done here in MME, Metallurgical Materials Engineering, my lab, the Polymer Extrusion Lab. And I titled the presentation saying more than just strength, and we'll get there, albeit the first few examples of making composites deals more with strength reinforcement. And hopefully this is a different point of view for you, and it kind of enriches the whole viewpoint you all will have in terms of composites compared with like laminate composites. A lot of the design for composites is geared around this simple equation. So the yield strength of your composite equals the volume fraction of your matrix times the yield strength of your matrix plus the volume fraction of your reinforcing agent times the yield strength of your reinforcing agent. Not too terribly hard of an equation. You want to think about, is it a law of averages or a rule of mixtures? And we'll talk about this a little bit more. But law of averages or rule of mixtures, kind of two equation types that we talk about when we make a final product out of two or more constituents, basically. Additive manufacturing of composite materials. Messed up my punctuation there a little bit, but additive manufacturing of composite materials, it's something I've been doing for a long time, and it's quite interesting. So if we take a look at this equation here, we're saying the yield strength. So think of a tensile test where you're pulling and you want those fibers to be oriented in the same direction as your applied stress. What's actually kind of cool with additive manufacturing, and I'm talking about fused filament fabrication additive manufacturing. Let me get this slide out of, or that animation out of the way. You can actually control the raster direction. So theoretically, you can control the direction of your reinforcement. And in this case, it's not continuous. There are companies that make continuous fiber reinforced printers, but we're talking about chopped fibers here, okay? And you can orient these chopped fibers in direction of your raster pattern. And so I've tried to depict the raster pattern path with this arrow. And so if we're going this way, we would align our composite, interior composite that way, so it'd be stronger when the applied stress is going horizontally. If we printed this way, kind of like my little snake pattern goes, we'd want our applied stress going, I guess, commensurately or parallel to that direction. And you could alter it. And we have this micrograph here of chopped carbon fibers we've thrown into a particle or a polymer matrix. And you can see they're coming out here. So this top part, the raster is coming in and out of the screen. And so you can see how the fibers are. And you also see they pulled out. And we'll talk a little bit more about that later. And going this way, they've aligned with the print raster going in this direction. So one layer came in and out of the screen, the other layer went this way, so parallel with the screen, and then the other layer again came in and out of the screen. So we had alternating print layers, and you can see it aligned the fibers pretty well. Other things you can see, especially if you follow my laser pointer, you can see there is some not very good adhesion between the chopped carbon fibers and the polymer matrix. And there are ways to manipulate the matrix to adhere to the, manipulate the filler to adhere to the matrix better, excuse me. And one way is chemical functionalization, and another way would be to try to increase the mechanical bond. And I don't talk about increasing the mechanical bond too much in this presentation. I'll verbally tell you on this slide. You can stew chopped carbon fibers in sulfuric acid to kind of chew up the surface a little bit to kind of create more of a mechanical bond with the matrix and the filler. So that would be altering the filler material. You could also do things and add things to the matrix material to make them more compatible with the filler, make them stick better to the filler. Because this is like kind of very similar to classical examples of fiber pullout and when composites fail. And I kind of added this little apology here. I don't have a micron marker on this micrograph. It's very uncharacteristic of me, so I can't really tell you the magnification. But the point of the micrograph is showing you that the fibers were aligned with print directions, so it serves its purpose. The matrix material we're going to talk about first in some work. So again, we're talking about a little bit about plant fiber reinforced composites we did here. The first matrix material I'm going to talk about is polylactic acid. PLA, it's not the best material, but there are some advantages to using it. Okay, so it's sustainable. It's sourced from sugar sources. So corn, mainly in the US, corn, we grow a lot of corn. Beets and sugarcane are primarily used in Asian nations, where I guess they grow a lot more of that kind of crop. It's biodegradable, so sustainable, which is a big deal. You don't use petroleum resources. It's sourced from kind of renewable resources, and it's also biodegradable. The drawback is it's not exactly an engineering plastic. So the primary application for PLA is actually food products. It is used in several biomaterial applications like stitches. And it also has shape memory properties, which actually makes it good for stitching. So you can stitch a wound very loosely, apply some heat, and then it draws the edges of the wound together. And it's kind of interesting. But we can change the fact that it's not exactly an engineering project, engineering plastic, by making composites. And so the filler material we used at first was jute plant fiber. And so again, jute, a kind of renewable resource. I'm going to pose this question to you. If I make a composite that is 2% by volume jute plant fiber and the balance PLA, what is the theoretical yield strength of this composite? So ask yourself this question. You might see something similar later. Things you need to know. So you for sure need to know what the yield strength of jute is. So it's 250 megapascals. Forgive my small p. I see that error in a lot, actually. And the yield strength of PLA is roughly 47 megapascals, depending on molecular weight and other things like that. But let's just go with 47. You will have to assume now that the interface between the matrix and the filler is robust. And that's a big assumption, because if you saw the micrograph on, or recall the micrograph on chopped carbon fiber in the polymer matrix, you saw there was some pull out. And glass fiber reinforced composites were probably one of the first things that we saw in terms of I guess society, in terms of a polymer matrix composite. And the first thing that happened was the glass fibers pulled out, and it was Owens Corning who developed some of these procedures to improve the fiber matrix interface. So right now we're assuming the interface between the matrix and filler is robust. We're also going to assume that the fibers are oriented parallel to the direction of applied stress. And we're going to use this equation that we saw before. So the yield strength of our composite related to the volume fraction of our filler and reinforcing agent, sorry, matrix and reinforcing agent respectively. So this is the volume fraction of the filler, yield strength of the, volume fraction of the matrix, yield strength of the matrix, volume fraction of the reinforcement, and yield strength of the reinforcement, All right, so we do some little math. If it's 2% by volume jute plant fiber, we know that it's 98% PLA, and we get this number. So 51.06 megapascals for our composite, and it's actually probably too low to see a difference in a sample set. But the thing is, any higher would clog a printer. Okay, so let's start talking about considerations we want to make when we're making composites. And one of them is the limitations imposed on your materials by the manufacturing process. And if you go back, I should have had a better slide about FDM, but I think a lot of people are familiar with this. You're squeezing molten plastic through a very small orifice. Usually it's less than 1 millimeter in diameter. Sometimes it can be 0.1 millimeters, a very small orifice. So if you have stuff that's going to clog it, you're going to have some troubles. And so that's one thing to consider is the manufacturing process. What else would you want to consider? You know, how you're going to mix the polymer and plastic with itself, right? How you make your composites. So some people use hot pressing, and we use melt compounding, and I'll play it. So you feed your material, hold on one second. You feed your material here, goes through the extruder, cool it off, and we wind it. So we have a filament that's ready for our 3D printer platform, basically. So we can go direct from melts to filament. And we can also chop it up later and make different types of material systems. But you feed your material through a hopper, melts it, goes through some sort of cooling. Sometimes it's water, sometimes it's air, sometimes it's both. And this is called a belt puller to try to maintain the diameter. And we have other components too that help us with diameter control. And then we wind it. So that's how we've made pretty much every composite in this talk using this extruder or another. Basically, we have other kind of smaller types as well. AM, so in the area of composites, characterizing AM or AM fabricated parts makes things less straightforward. So additively manufactured parts are less straightforward to characterize. And so it's not just a matter of this equation. And some variations that we have, so different print orientations will have different mechanical properties. So if you print it flat, it's going to be stronger than if I printed it vertically. And that's because there's failure in the inter-aster interface. And improving that interface has also been another subject of our work. And we'll talk about that a little bit as well. Here's a UTS graph for polylactic acid. And so if I print it vertically in the ZXY direction, it's in this case roughly half of what we got in the XYZ. And we had kind of some high yield strength values because of the grade of material we were using when we made this graph. So it's a little bit higher than the problem that we worked out just now. When you print something, so imagine the print nozzle comes in, and on the edges you have a longer dwell time than you do in the middle. And so let's just say we were printing this way. On the edges it's going to make a turn, so that heated nozzle is going to be diffusing, causing polymer diffusion longer. And so you have a more robust adhesion between layers on the edges because of more heat. And some people would say, well, if you want to make this better, why don't you just print hotter? Well, it doesn't always work that way because sometimes you print too hot and it comes out like water, and so you won't be able to hold your form. Have a micron marker on this one, so that's good. Other materials used in this effort, so we used salt, we used palygorskite organo-nanoclay, and organo-nanoclays have been used pretty extensively for polymer strengthening, making composites. Mortomorlite is another one that's been used in literature. It's been shown to halt creep. I got in the palygorskite because UTEP used to actually have a company called Mayan Pigments, and palygorskite is what's responsible for Maya blue. And so I had some interest in it. I thought it was kind of cool. And we actually used two different colors of organo-nanoclay in this work, and I'll show you. By salt, I mean regular old NaCl. We used reagent grade. We didn't get it from the dinner table, but salt. And that was kind of an interesting thing, and we'll see the results there. And also salt to functionalize jute, and so we'll see some of that on the subsequent slides. And again, functionalizing is when you alter your filler material to essentially make it stick to the matrix or make it more compatible with the matrix. You want to make that matrix filler interface very robust. Here's some scanning electron micrographs, or SEM micrographs of some of this stuff. So PLA printed very well on its own. If I were to do some failure analysis, I'd say this is a brittle fracture mode. We don't see that much evidence of plastic deformation. There's evidence of craze cracking, which is the primary failure. Anytime you take a piece of plastic and you bend it and you start seeing some white, that's called strain whitening, and that's a bunch of craze cracks forming. If we look closely at the PLA jute composite, we see that it didn't stick very well, that we also have fiber pull out. Also adding the jute fiber, we see a little bit more plastic deformation, even though this is a different mag. But we see some plastic deformation and even some voids. So maybe, you know, this fiber was kind of outgassing and causing problems actually. When we look at salt, we see that the fracture surface again is pretty brittle, but the salt seems to have stuck pretty well to our polyester, to our polylactic acid, which is a type of polyester. And we have SCM of one of the Mayan pigments. So Maya Chrome is the company, chrome like chromatic. And so PLA Maya Chrome Blue, we added about 2% by weight. I didn't add that little detail. We see a little bit more plastic deformation on the fracture surface. So it did something to the surface, but if you look closely, you see there's a lot of voids, and in the voids are probably the Maya Chrome particles. And so that means they actually concentrated the stress. And we see kind of these circular things called strain fields that kind of manifested around them. So looking at the micrographs, I wouldn't expect the Maya Chrome to have had that much of a profound effect on the strength in a positive way anyway. And maybe even the jute probably didn't do that much for us either. Kind of this arrow again, just in case I'd forgotten to mention, fiber pull out, not a very good interface. So pay attention to that. Learn to read the micrographs. It's always really, really good if you don't already know. Tensile test results. So I almost could have predicted that the Maya Blue and the jute fiber, and I kind of did predict it, and not just remembering the results, lowered the strength. Didn't do that good of a job. I didn't show the SEM for Maya Chrome Yellow because I couldn't find it. So I need to do a better job organizing my scientific data. That's a big no-no. Let that be a lesson. But also, didn't have much of an effect. We see a slight bump in the mean, which is what this bar tells us, but still statistically significantly the same. And the salt also kind of bumped up the mean a little bit compared to our PLA control specimens, but still not statistically significantly different. So that's what these circle graphs tell us. In terms of percent elongation, it was actually kind of interesting. Adding the jute kind of plasticized our material. And so we had a statistically significantly different data set in terms of percent elongation for the jute fiber. So it made it more rubbery, basically, albeit not that much, but still it was noticeable and statistically significant. Salt, though, started piquing our interest as a research group, and we started looking closer at the micrographs, and we can kind of notice some things, and I'll highlight them with the arrows. So let's go back. So if we look at this fracture plane and this fracture plane, it traverses the interface between the matrix and filler. Excuse me, I lost my train of thought there. And so that tells us that there was pretty good interaction between the salt and the PLA, actually. And from the point of view of crack propagation, they were the same material, at least in that area. And we see in other areas, salt I expect to be fairly brittle, kind of cleaved and stuff like that. But it started getting our interest up. So we started looking at other things too, like what did it do to anisotropy? Okay, so the salt now, it adheres to the matrix really well. What if we get salt on the surface and we improve the inter-raster interface when we print in the Z? Okay, so if we look at this, we printed these in the Z. Okay, so all our layers are going this way. And these layers alternated X and Y. So some of the layers were going parallel with direction of strain, and some of the layers are going crosshatch to the direction of strain. And that's what X and T means. That's not what these two data pools mean. Okay, so T here means it mimicked printing in the Z, and X means we printed it alternating rasters. Okay, so we lowered the difference between Z-like printed specimens and something with a different raster pattern. So we decreased raster pattern sensitivity, basically, by adding salt. So that was pretty profound. So we made a composite that decreased anisotropy. So that's pretty profound. It's pretty cool, especially in the additive world. We decided to then use it as a functionalizing agent. And so we noted before that these fibers kind of pulled out and they didn't stick very well to the matrix. We could have done a better job separating the individual fibers as well, because you see there's these big agglomerates, but then you have these smaller ones. And the smaller is generally better when you do some of this stuff. And it's kind of a paradoxal theory that we may touch upon later. When we did functionalize it, this is functionalized, we noticed this, and this is called fibrils. And so the fiber still pulled out, but the plastic didn't want to give it up, basically. So the plastic held on more to the fiber and formed these fibrils between the fiber and the matrix. So we actually improved the matrix fiber interface. What was interesting, though, is that it didn't really have an effect on the yield strength. So statistically the same, but it did remove the plasticizing effect that the jute fiber was having. So we maintained the level of stiffness. So this may bear further study, but we were able to detect some difference in the mechanical properties by altering the difference in interface. However, it didn't manifest in terms of yield strength. So things don't always manifest in terms of yield strength, which is kind of another point of the stuff I'm talking about today. Other physical aspects we wanted to look at, instead of using just a tensile test, we used a dynamic mechanical analyzer, or DMA. And I won't go too deeply into dynamic mechanical analysis in this lecture. I will have probably a subsequent lecture where I talk about dynamic mechanical analysis in depth. But basically, there's different bending tests you can do, and there's actually a whole slew of tests. You can actually do straight up tensile tests in the DMA. It's actually a very powerful little instrument. Here's the model I have in my lab, and you can hold it in place either with in 2 points or 1 point, and then you have another mechanism that actuates it basically, and then you actually increase the temperature over time, and you can actuate it at different frequencies as well. We typically use 1 Hertz for most of our tests, but quick thing, it's kind of a mechanical test. You heat it up, so it's a thermomechanical test in reality, and from that you can get rheological information like glass transition temperature and dampening characteristics of your material. A typical DMA curve, so I look at these 2 curves, and it should be storage modulus, not just modulus, so I made a little mistake there. But we look at 2 main data points. There's other stuff you can look at, but when we're caring about glass transition temperature, and my mouse is lagging very badly, here we have glassy onset, and that's determined by storage modulus, and the end of glassy behavior is determined by the max 10 delta, basically. And so those are kind of 2 key things we look. The window between glassy onset and the end of glassy is basically the window where your material is going to flow like glass, basically. And at the end of glassy, it kind of melts, basically. So it's more like water. And that's just kind of a quick overview of DMA. So our DMA results, let me move the mouse out of the way because it's lagging today. I don't know why. So we have PLA, myochrome, and salt and jute, and there was slight effects on the glass transition temperature, but what it had kind of more profound effects on were the window, and so it changed it basically. So it increased the window, so it allowed it to kind of suppress melting, basically, is kind of what I'm trying to say with my words. All right, so from the DMA data, we can also tell things. So here, more energy was absorbed by the PLA, and so PLA itself is actually a better dampener. What we did by adding this other stuff to it is we made it act more like a spring, and so it would store the energy instead of dissipate the energy. So depending on your application, that might actually be a good thing. And then the pigments are also altering the rheological behavior. And so we see that our viscosity drops when we add the pigment. It drops a lot more for the jute, but everything actually decreased the viscosity. So other things you look at other than mechanical strength, what other things did it do? Well, it change the energy dissipating behavior of our material by the stuff we added, some more than others. So it's kind of interesting. And so it's always good to subject composites to a full gambit of testing, depending on the application, of course. Here's another article that I kind of want to talk about, or an article I want to talk about. We've not talked about articles just yet. But hybrid metal thermoplastic composites, also for FDM type manufacturing. And this is a paper we put out in 2019. And generally in composites, the morphology of the filler material is static. So if we revisit the slide on chopped fiber, that chopped fiber looked like a chopped fiber before we processed it and combined it with plastic. It didn't look much different before and after. We wanted to see what would happen if we used materials with similar melting temperatures as the glass transition temperature of our materials. And so we started off with these spheroids, and we used tin bismuth powder, which is basically a solder. They had a nominal diameter of roughly 10 microns, and so they were pretty small. And so we blended that with our trusty extruder. If you look at the phase diagram for the composition of tin bismuth we use the eutectic tin bismuth. So the range of our extruder and printer processing would liquefy the tin bismuth. So we had the opportunity to change the morphology from a sphere to something else. We used 3 matrix materials here. So we used ABS. We used a blend of ABS and SEBS. And SEBS is a styrene, ethylene, butylene styrene, and it's used a lot in like BMX bicycle grips and the soles of shoes. We actually used in the article, I won't go over them all, but we used 3 compositions of that blend. And our old trusty PLA. And ABS is generally what Legos are made out of, acrylonitrile butadiene styrene. So let's see what happened. So if we look at the data, so again, I'm using my Tukey-Kramer circle graphs to kind of help me discern which experiment was better. And F means functionalized, NF means non-functionalized, and we had ABS control. So we functionalized, we had 2 data pools. We had functionalized tin bismuth, and we had non-functionalized tin bismuth. And initially we thought that the temperatures would kind of negate the functionalization, but in this case, they didn't seem to. Okay, so we kind of had a sweet spot in terms of composition. So putting in 10% by weight tin bismuth was too much, but 5% actually showed a strength increase. And we see that both in our Tukey-Kramer graphs and our stress strain curves. And we see that ABS on its own was actually pretty elastic. And so we had, maybe 18% elongation. And I can kind of see that a little better if I look at this. So the mean, yeah, I'm going to guess around 18 in terms of the mean. So these stress strain curves are actually, we made composite stress strain curves in MATLAB where we plotted the average of all our tests. So it was actually kind of cool. And so this guy was the standout winner in terms. And again, functionalization played a role. What happened? Well, we drew from something spheroid into something kind of wire-like. And so this is a scanning electron micrograph. It's kind of cool. You can actually see the microstructure of our tin bismuth. Based on the size, this might actually be an agglomerate of 1 or more. But we still changed the morphology from that of something spheroid to something wire-like. If we look at the other compositions, so this is one of our ABS SEBS compositions, and I'm sorry for the kind of blurriness of the graph. We noticed something different here. One, we noticed that, yeah, we got wires drawn, and even here, we did change the morphology even on the kind of top surface. So we looked at it crosswise, so the transversal reason, right? Well, we looked at it this way. I might be getting my terminology wrong. And if we looked at the other section of our, this is actually just the filament, we see that we had wire drawing. And so, again, we see that we drew, but when we compared the sample pools, we saw that the non-functionalized actually was the winner. And so functionalization does not always provide a benefit. So we showed a scenario where functionalization provided the benefit. We showed here another situation where functionalization does not provide a benefit. And it should note, though, so why didn't it have a benefit? Well, the SEBS has other additives, and it was actually grafted with something else called maleic anhydride. Maleic anhydride is a derivative of maleic acid. It's from apples. It's also found at the bottom of old wine barrels. And what it does is it actually makes polymers compatible with non-polymers. And so you can make it stick to things like metal. And so our hypothesis here was that the maleic anhydride graft was somehow compromised by the functionalization process. And again, this is something else that bears further investigation. That's the trouble with scholastic research. Sometimes people graduate and the project dies after they're gone. So sometimes I revisit old stuff and rehash it later. And that's what it's all about. So anyway, that's what may have happened here. So here we see a case where functionalization was beneficial. We saw an increase in UTS. Even though I promised we're not always going to talk about strength, we're still talking about strength. Here I see a situation where the functionalization perhaps was detrimental to what was already there in the matrix. So something else to consider, the chemical compatibility between your filler and matrix and how you may be altering that as a materials engineer. PLA was interesting because it didn't actually show a big strength increase. And in fact, the non-functionalized did not show any strength. It was actually detrimental, and the functionalization barely a little bit of a kick. and it did compromise the flexibility of PLA, so we actually lowered the percent elongation. So we actually made it stiffer. So we maintained the strength, made it more stiffer, which may actually be good in other applications. But if you look close, we actually drew rod-like structures. So the drawing was more profound in the PLA than it was in our ABS or ABS-SEBS blend. And so the matrix material interaction with your filler material, whether it's sticking, whether in this case we're kind of doing a hybrid material. And I should point out, this was published in a Journal of Thermoplastic Composites, so it's quite fitting. The interaction of the matrix material with your filler material, whether it's a sticking thing or changing the morphology of it based on some sort of viscosity thing, are all aspects you have to consider. So it's a very, very complex subject, if you will. So things to consider when making composites. I was going to put an icon, I'll just put myself. Things to consider when making composites. So the manufacturing method of the final product, compatibility between the matrix and filler, how you can improve the matrix filler interface. And so kind of three ways. So manipulate the filler, manipulate the matrix, and sometimes both. And sometimes it doesn't work out if you do both strategies. All right, so we can make composites to enhance more than physical strength, which was the purpose, oopsie, which was what I wanted to get to when we talked. And I have a video that I'm trying to get to play. I apologize. There we go. May edit that out. All right, so here we've made a ferromagnetic ABS composite, and so what we loaded magnetite into the material to make it able to respond to a magnet. So ABS on its own is not going to respond to a magnet. We've added something magnetic to it, so we can make it respond to a magnet. The beam it's on is one of our rubberized blends, so one of our ABS-SEBS blend, and so we're using kind of two not off-the-shelf material systems to make something new. That's what it's all about. But here, this is just a very simple example of we've made a composite. We didn't care about the physical strength at all. We wanted to make it so our polymer responded to a magnetic field. Okay, so we made a composite to respond to a magnetic field, so we made it respond to electromagnetics, basically. On the subject of functionalization, so this will kind of be a segue into something else, also EM related or also electromagnetic related. We typically use chemical silanes, which is this big molecule here, to functionalize our material. And what we're doing is we're essentially making hydrogen bonding between our matrix and our material. And so this micrograph, kind of maybe doesn't look that much different than this micrograph at first glance. But if you look at the scale bar, it kind of tells you something. So we added the same amount of this case we're using titanium dioxide because we wanted to change the dielectric constant. We're using the same amount of titanium dioxide in both material sets. However, for the functionalized, we've treated our titanium dioxide first with this silane, and there's many types of silanes. The people that make silanes tailor them for the material that you're working with, for the matrix material you're working with. So you can have a different chemical silane for PLA than you would for ABS and other polyesters, also polyesters that we've used in the lab. So PLA is a polyester, ABS is a copolymer triblock. So kind of different types of polymers. So you use different functionalization agents for either a polyester or a copolymer. So non-functionalized, we see that we have these kind of big agglomerates, and functionalized, we still have agglomerates, but they're much smaller. And we kind of did a size distribution, so we were roughly 30 microns for our agglomerate size with non-functionalized. And functionalized, we were on 10 microns, so about half to a third the size. However, if you look at how small the individual particles actually are we may still have a little bit of ways to go. So you maybe want to ball mill your material or something to help increase the dispersion within the matrix before compounding. So you could do something where you blend your polymer in pellet form perhaps with your filler material in another way. So still a little ways to go. So they're actually quite smaller. And so this is actually your particulate size. So it's pretty small. If this is 500 nanometers, maybe this is almost this is nanoparticle. So anyway, but we did achieve a bump, and we actually got better as time went on. So if you look at this, the filling is much higher here than it is on this micrograph. So we actually got better making a high K material. And so we're basically making better insulators. And this graph actually corresponds with this work. And even with a low loading, so this is probably like 5%. You could do a back of the envelope calculation, maybe throw this image in ImageJ and compare white to black and remove the air gap there. But we're close to 50%, 60%, I'd guess, just by staring at it on this one. Anyway, this graph corresponds with the previous micrograph, so we were able to achieve a bump in our dielectric constant. So ABS alone is roughly 3.2. In some cases, people have it higher, but this is where we are. This is where we wanted to get, but again, we're using additive manufacturing, so it leaves air gaps, so it actually lowers the overall dielectric constant. But there we go. So we've seen one application where we're making EM structures or EM materials, electromagnetic materials, basically by making a polymer matrix composite. Another application was X-ray shielding. And here's an article we had put out a few years back where we made 3D printable X-ray shielding, and we used polycarbonate as a matrix, and some pretty widespread characterization was used in this. We used XRD to make sure we weren't making oxides. And so polycarbonate is a semi-crystalline material, and so we actually get a somewhat of a peak, although it's broad, but it has not quite an amorphous halo. And so we can talk about polymer crystallinity as well. But we have our tungsten peaks present in all of our scans. And so the tungsten peak showed up in the tungsten powder, and the tungsten peak also showed up in the PC tungstrate. And we wanted to make sure we weren't making tungsten oxide, because tungsten oxide would have a different property, different X-ray shield property. And the X-ray shield properties are tabulated. So you use Beer-Lambert law, and if we see this in Intro to Engineering, we also see this in structural characterization. And so the transmitted X-rays is equal to 100% basically, which is the intensity of your incoming beam, e to the rho, or sorry, mu over rho, which is the mass absorption coefficient times the density of your material. So density will cancel out, but tabulated values of mass absorption coefficient are always given mu over rho. And so by convention, you always have to have something to cancel it out, times x, which is the thickness of your material. And so you can calculate a new mu over rho for your composite by just saying the weight fraction. So this is mass fraction, sorry, mass fraction of component 1 and mass fraction of component 2. So I'll give the answer for the other question here. Is this a law of averages or rule of mixtures type of equation? And so if it's weight percent, it's law of averages. So this is weight percent. The previous equation we saw earlier, our composites equation, uses volume fraction, so that's rule of mixtures. So if you didn't already know it, that's the difference between law of averages and rule of mixtures. And here's some results. So we have our straight up polycarbonate. It was white in color. When we add 1% by weight tungsten, it starts getting darker, and we were only able to go all the way up to 5. We tried to save our processing equipment. So tungsten's very hard. We didn't want to eat the inside of our extruder, so we didn't go that high. But you see, polycarbonate on its own already blocks out X-rays pretty well on its kind of interesting. So if you're in a pinch and you have a lot of polycarbonate and you want to shield yourself for some X-rays, you'll actually do a pretty good job. Adding 1% by weight tungsten decreased it pretty significantly, 3% and then 5%. With the error bar, we're about 3% transmitted X-rays. So made a composite, didn't necessarily care about strength. We cared about X-ray shielding. Okay, and these were the results. Another thing we looked at was heat conduction. And can you manipulate the heat conduction by additively manufacturing composites, basically? And so we had ABS alone, ABS loaded with graphite, ABS loaded with carbon fiber, and ABS loaded with silver, so a pretty conductive metal. It's kind of an expensive composite if you think about it. So it's hard to kind of see it. And let me get my laser pointer back. ABS, graphite, carbon fiber, silver. I was mousing over. I don't think you guys saw it, so I apologize. But if you compare graph to graph, you see that the scale is different. And so two different planes, so Z plane, XY plane. The orientation is not that important right now. Just know that they're different planes. And so we see a difference. Even ABS by itself will conduct heat differently. And graphite, had kind of a bigger, actually not much of a difference, no, bigger peak. Sorry, I'm having trouble reading my own graph, excuse me. But anyway, there is a difference between the planes for thermal conductivity. And again, kind of similar to how we saw with those carbon fibers, we see a difference in morphology, printing right to left and printing in and out of the screen. So we were aligning the stuff. And so that's why the heat transferred in a different way. Okay, so another application of polymer matrix composites, particularly for additive manufacturing, you could conceivably create pipes for thermal dissipation this way if you just by controlling your raster pattern of your composite. So kind of summary, so points of view to consider when you're making polymer matrix composites. So from the matrix, manufacturing constraints, chemical compatibility, and can you have mechanical bonding? That probably goes more into the filler. You can look at it either way. Filler morphology, compatibility with the matrix, and the effect on overall physical properties. How much is enough? How much is too much? If you saw with that tin bismuth experiments, 10% by weight was too much, but 5% was pretty much Goldilocks, so it actually improved the strength. And so hopefully you guys have enjoyed this overview basically of thermoplastic composites, and kind of considered things other than strength that you can manipulate by making a composite, which is kind of the point, and also thought of some things from an engineering point of view that you want to consider if you get in the business of making composites. And if you have any questions at all, always feel free to ask. Thank you. Thank you very much.
Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.